Alright gang, here we go. This is for Chem 2 Unit 5, very tail end of it. We're going to be talking about something completely new-ish called molecular orbitals. Okay, now just let's take a step back to I think Unit 2 when we talked about electrons and we talked about orbitals. Remember we had our s orbitals, we had p orbitals, and then we had, d orbitals, and then we had f orbitals. Remember that the shape of these orbitals were like this. We had s was spherical shaped. This was a sphere. P's were always dumbbell shaped, and they always came in sets of 3. Remember, we could have some on the x, some on the y, and then some on the z axis coming in and out of the plane. And then you also had so you had, we'll put like 3 of these, 3 times of those. And then with d orbitals, they were the cloverleaf shape, right? They were like kind of like this, and then also like this, right? And you'd have 4 of those, and then one more that was the funky donut one. So you had like the ring, and then the p orbital. Those kind of do this, like that. And then the f's were all sorts of weird things. We had 5 d's, and then we had 7 f's. All right. Now remember, the shapes of these guys were all determined based off of Schrodinger's wave equations, and we use this symbol here as the Greek letter psi in order to talk about the wave equations. And so these wave equations allowed us to predict what was going on with our electrons and allowed us to predict the location of those electrons. Okay, so that's that, right? All right. Now we also use these ideas of these electrons. In the last video, we let me see here. We talked about how we had this idea of the valence bond theory, okay, that when 2 electrons or 2 different atoms bond with one another, this bonding occurs because their valence shells are literally overlapping with one another. So if you had HCl, right, H bonded to a chlorine, the H was its 1s orbital, right? This would be the 1s. There's your little nucleus. And then your chlorine, there's your nucleus. The chlorine would be bonding with its 3p, right, because it's on the 3rd energy level, and the p is where those valence bonds are, right? And so your P would be like this, and then this area right here, that overlap, that's where the bond occurs. So that's what the valence shell theory is talking about, okay? And we can make all sorts of different series, and to learn more about that and hybridization, okay, and this led to the hybridization theory, right? Watch the previous video. Hybridization is kind of what this was all about, all right? Now, in molecular orbital theory, which is what we're going to focus on today, life gets a little bit more complicated. Now, what I want you to focus on as we're talking about this is a great example of how a lot of times in science we, have data and models to represent what's going on, and we develop theories to explain the data that we find, right? And then we can test those theories. And these theories, sometimes there's more than one theory that is good at predicting different types of situations, and it's really just our way of being able to understand what is going on. Okay, and so we had the valence bond theory, which was really good at certain things, and then now we're moving on to the molecular orbital theory, which is good at other things, but not as good or at some things that valence bond theory was. But anyway, so molecular orbital theory. Okay, now molecular orbital theory is, again, it's based off those wave properties of atoms. Okay. Now, we use the wave properties, right? These wave equations, the ability of these electrons to move as waves, right? They go along and they sit there and they act like standing waves, okay? And we can use that idea to come up with these things called molecular orbitals. And it's essentially a lot of the same things as what we learned about atomic orbitals, okay? There's still a maximum of 2 electrons per orbital, okay? Electrons have to have, if you have 2 electrons per orbital, and those 2 electrons have to have opposite spin. Okay, opposite spin. That specific orbital, whatever you're talking about, has a definitive energy level. Okay, and we can visualize the electron density by a contour diagram. So same thing we've been doing, the general shape like peas or dumbbells, so these have different shapes in and of themselves. Okay, now here's where they're different from atomic orbitals. The big reason is because the molecular orbitals are the orbitals for the entire molecule. Okay, so it represents where all the electrons might be for the entire molecule, as opposed to the atomic orbital would only show you where those electrons are for that specific atom if that atom was existing in space by itself. Okay, and so when we start combining, so essentially what we're saying is we're going to take the idea of these valence shells, that they do in fact overlap to form bonds, but when they overlap, they you actually get this crazy wave interaction. Now, if you've taken physics before, you're definitely familiar with this idea of constructive versus deconstructive interference, right? In constructive interference, you've got two waves that hit each other, and when they're constructive, they build each other up and they make themselves taller, right? And then if they're deconstructive interference, they go together and then they cancel themselves out, so they're completely knocked flat, okay? And so we get that kind of idea because these electrons are coming in and they can hit each other and they can combine in two different ways. They can combine in constructive combinations, and if they combine in constructive combinations, they form bonding orbitals, and that's what this guy is here, these bonding orbitals. If they combine in destructive combinations, then they form anti-bonding orbitals. Okay, and when they form anti-bonding orbitals, okay, they form this new thing called a nodal plane. Now, we've seen nodal lines before, nodal axes or nodal points, but now we get a nodal plane. All right, so this is an entire planar region, the 2D region, where there's absolutely no electron density, which is kind of a new thing. All right, so here's kind of the general, most basic what it looks like. So if we have two hydrogen atoms that are combining, here's the 1s from hydrogen here and the 1s from hydrogen here. All right, now valence shell theory, we would just say, well, these two guys are going to overlap, and then those two places that they hit, right? So this would be 1s, and this place in here, that's what we said in the previous video. That's what the hybridization theory, the valence shell theory says. That's how bonding occurs. Now, with molecular orbital theory, we actually form something new. Now, we do say these are sigma bonds, right? Because they're direct overlap right across, and the density is right across this internuclear axis. Okay, so there's your internuclear axis, and your density is right on that. So this would be a sigma bond, okay, or a single bond. All right, now when these combined, because we use two atomic orbitals, we're going to form two new molecular orbitals. One of these is going to be called the bonding, and the other one's going to be the anti-bonding orbital. All right, the bonding orbital is down here, and we call this sigma 1s, right? It's sigma because it's a sigma bond, and it came from 1s orbital, so that'd be sigma 1s. And then the anti-bonding is the sigma 1s again, but it has the star, and so this is pronounced sigma star 1s. Okay, and so this would be the molecular orbitals of a hydrogen atom as they bond, right? So you have the constructive versus the deconstructive combination, all right? Notice that the electron density is in different places. In the bonding orbital, the electron density is between the two nuclei. In the anti-bonding orbital, the electrons are separated between the two of them. All right. Okay, and so now we get this thing here that's really kind of what it all means energy-wise. Okay, we get the energy level diagram. They're also called molecular orbital diagrams. Okay, and they actually show how the orbitals combine, from the individual atoms combine to form the molecular orbitals. Okay, so on the left side here in yellow and the right side here in yellow, we have the original s orbitals from the hydrogen atom. So we have a 1s and a 1s from these hydrogen atoms, and then they're going to combine. So in the middle is where we show the molecular orbitals, right? And so in the bottom, because the bonding orbital is a lower energy because it was a constructive interference, okay, then this is going to be lower in energy, and this would be the bonding orbital. So this is your sigma 1s, all right? Okay, and then up here, you have your anti-bonding. This would be your sigma star 1s. Notice that there's a big energy gap here between the two, all right? When you're filling these out, your electrons, right? Hydrogen came in with one electron here. Hydrogen came in with one electron here. You're always going to fill them in bottom to top, okay? So your two electrons, one go here at the bottom, the other here go in that bottom, and you're good to go. There's no more electrons here, all right? So this here, this essentially, well, this whole thing is the molecular orbital diagram, exactly what we're looking at. If you take out just the orange boxes and just write out that much, then that would be the electron configuration for the molecular orbital, okay? Because it shows where the electrons are for the molecular orbital. So it's essentially just like electron configurations you've done in the past, only totally different, okay? All right, and then we have this new idea called bond orders. Now, bond orders are super trippy, but super helpful, okay? This is how you calculate it. You take the number of bonding electrons minus the number of anti-bonding electrons and divide it by 2, Okay, so you take the number of bonding, which is 2, minus the number of antibonding, which is 0, so that's the 2 minus 0, and you divide it by 2, and you get the bond order, okay? And so this has a bond order of 1, okay? If your bond order is 1, that means you have a single bond. If your bond order is 2, that means you got a double bond. Bond order of 3 is a triple bond. Bond order of 0 means absolutely no bond at all. Now, here's where it gets trippy, okay? It's all of a sudden, we can start having halvesies bonds, okay? So you can actually you can do the math and come up with a half a bond, okay? A bond order of 1/2. And so that's that's like a weak bond. It's a bond that's not quite a sigma bond. It's not quite a full bond, but it still has some attraction force dragging those two together. You can also have like 1.5 bond order, which would be like a full single bond, that full sigma bond, but then another halvesies towards a double bond. So you start to get some weirdos, okay, that kind of have a little bit more characteristic of a double bond, but not quite all the way. All right, so let's look at another molecular orbital diagram for something that we should already know how to do. We know that helium does not exist. Or diatomic helium does not exist, right? It's a noble gas. It's never going to form a diatom. There's absolutely no reason for it to do so. So our molecular orbital diagram and bond orders also predict this. If we were going to write out the molecular orbital diagram for helium, H2, trying to make it combine, it would look like this. Notice that it looks exactly the same as hydrogen, only now the helium atom came with a full 1s orbital, right? 1s, 1s, both of those are full. And so these 4 electrons, 1, 2, 3, 4 here, are going to be shuffled into the bonding 1s, and then also the anti-bonding sigma 1s. Okay, and because these are both full, all right, your molecular orbital is completely full, and so your math would turn into your bonding minus your antibonding, which would be 2 minus 2, and then divide by 2. So 2 minus 2 is 0, and so you have 0 bond order, so you have 0 bonds whatsoever. Therefore, you can never have He diatomic fully exist. All right, okay. All right, let's see. Okay. Let's do one of these real quick. Let's H2 minus. So if we were going to draw our molecular orbital diagram, let's see. So this would be a 1s, and then we have a 1s here. Okay. All right. And then these are going to form. So we're just essentially redrawing exactly what we've seen drawn before. This would be our sigma star 1s, right? And then this guy here would be our sigma 1s, okay? Now H2 minus. Now H2, each hydrogen here, we have to figure out how many electrons we have total to work with, right? So H2, each of them are going to come with 1, so we'll just go ahead and write in those 2 electrons like that. But then that minus sign means that we have an extra electron. So we're just going to add another electron. It doesn't really matter which one we put it in, okay? Over here, it does because these electrons these 2 1s's are exactly the same. Now we're going to put in our our electrons bottom to top. So we're going to put our electrons here. Our bonding is going to get these guys 1, 2, and our anti-bonding gets 1, right? So now we've used all 3 here. So this here would be the electron configuration of H2 minus. Okay, that would be the electron configuration. Bond order here, well, it's 1/2 times the number of bonding, which is 2, minus the number of anti-bonding, which is 1, so P2 minus 1, so it would be 1/2 would be the bonding order. All right, so, and we could go through and work through a couple of these, and I think you should. And really, it's pretty easy. Like, we already know that this guy here has a bonding order of 1, because we did that one earlier. We know this one's got a bonding order of 1/2. So you know the answer is already at least B, and you can do the other 2 and see what you can figure out. All right. So guiding principles for the formation of molecular orbitals. All right, so these are important principles that kind of make molecular orbitals what they are. Okay, the number of molecular orbitals formed always equals the number of atomic orbitals that are combined. Okay, all right, this is important. So if you combine 2 atomic orbitals, you're going to make 2 molecular orbitals. Okay, atomic orbitals always combine with atomic orbitals of similar energy. Okay. So if you got 2 different atomic orbitals, then they're combining, that means they're probably of similar energy. All right. The effectiveness of with which they combine is proportional to their overlap. So this is essentially what we already talked about. So if those 2 atomic orbitals, how well do they form a bonding and an anti-bonding orbital? It's completely dependent upon how much can they overlap one another. Okay. And one way we can help make sure they overlap more is by having very similar in energy levels. Okay, and then the last two are just reskins of two principles you've already mastered. Okay, first is the Pauli exclusion principle. So each molecular orbital can accommodate at most 2 electrons with opposite spin. Okay, 2 electrons with opposite spin. So you got, and inside any box, you always have one going up, one going down. And we did that right over there. Okay, and then Hund's rule is a reskinning of Hund's rule here. When filling molecular orbitals of the same energy, 1 electron enters each orbital with the same spin before you start pairing. So once we start having our pi, or 2p orbitals, we start having a little bit more exciting stuff going on. All right, so we have to keep track of Hund's rule there. All right, so let's just do another one here, see if we can figure out, okay, a couple other important things. So lithium, dilithium here. Notice that we did hydrogen, we did helium, and now we're doing lithium. Elements 1, 2, and 3. The reason we're doing that is because once you start adding more, and we'll just barely look at a couple more, once you start adding more, these molecular orbitals get really complicated very fast. So we're just going to keep it simple by working with like 3 or 4 electrons at a time. All right. So dilithium does in fact occur, but only at high temperatures, and this would be its Lewis structure. It would look like this. All right. Here's the molecular orbital diagram. So lithium's in the second energy level, so it's got a 2s orbital that has 1 electron in it, but its 1s orbitals are completely full. So notice this guy down here looks exactly like helium. Notice that, you know, the electron configuration for helium, the electron configuration for the molecular orbital diagram was exactly like what helium's is, right? So that's kind of nice. And then we have what's above it. So we got the 2s, those 2 lithium atoms are combining. They each have 1 electron, and they're going to form, and they're going to get into this 2s down here. And there's your anti-bonding sigma star 2s molecular orbital is completely empty. Now, one thing to take note of is remember this is going up in energy. So this level to this level here is your change in energy, your energy difference between your bonding and your anti-bonding. Notice that your 2s has a much bigger difference in energy between the sigma 2s and the sigma star 2s. There's much bigger difference in energy. Okay, as you go higher and higher along the to higher and higher energy levels, this distance between them gets bigger and bigger. All right, but really, what's really important is if we figured out the bonding. Okay, the bond order for this, we take the bond order would be 1/2 times the number of bonding, so that's 2, 4, minus the number of anti-bonding would be 2, and then divided by 2, so our bond order would be equal to 1. Okay. The other thing we can do is if we completely ignore all of the core electrons and only focus on the valence electrons, which would be up here, and do the bond order, what would we get? Well, we get 2 minus 0, and we'd get 1. Okay, so we can see that those core electrons don't really play a major role in bonding. They you got electrons in bonding, you have electrons in anti-bonding. They essentially cancel each other out. And so really, when you're drawing electrons, it's kind of the same thing as using the noble gas notation for electron configurations. You just kind of assume that they're there, but they're not participating in bonding, so we're just not going to write about them. Okay. Now here's where life gets pretty fun. Okay. All right. So so you've got your molecular orbitals from your p orbitals. Okay. Now p orbitals, remember, they come in three directions. You've got your p orbitals that's in your x plane like this, and you got the p orbitals that are in your y plane that are like this, and then you have your p orbital that are in the z plane, and they come in and out of the screen at you, right? 3 dimensions. Okay, and we talked about last time how you can form a sigma bond by having your s orbit or your p orbitals overlap end over end. So this p orbital, and they've arbitrarily said this is 2pz. This is the z-axis. It doesn't really matter, but you've got this sigma bond here. Notice how you've got this end over end overlap like this, and so you've got this is what your bonding and your anti-bonding orbitals look like for your p over end on end overlap. All right. Pretty wild. Now, this is where it gets crazy. Now, remember before when we talked about P, and I'm just going to draw one here. So we talked about how to form pi bonds. Remember that? You'd have two different p orbitals, right? One would be like this, and one would be like this, and then one would be like this, and one would be like this, right? And the bond would be occurring here. This would be your pi bond, right? And we talked about how they kind of stretch like that. And so that's kind of what we're looking at here, is the same idea, this sideways overlap, okay? So molecular orbital theory does, in fact, still support this idea of a sideways overlap by unhybridized p orbitals, okay? So you've got your p orbitals here, okay, and they get these sideways overlap above and below and then in and out of the screen like this. And so you get these two shapes, your bonding and your anti-bonding orbitals, like this, bonding versus anti-bonding orbitals. All right, pretty exciting. Okay. Now, the molecular orbital diagram, so when you start adding the p's, okay, so this is your 2s. Notice that we don't even write the 1s because it doesn't tell us anything new. Okay, so now we're looking at the p's, all right? So 2s looks exactly like you expected. So your 2p, remember you started with 3 of them. You started with your, and we'll just go ahead and lay these at z, x, and y, okay, and z, x, y. Kind of the same thing. So remember, z was our end over end overlap. So these two orbitals are going to form our sigma and our sigma star, okay, because those are your end over end, all right? And then 1x is going to form your bonding, 1's going to form your anti-bonding, and then your y, and then your y. And really, it doesn't matter so much if, like, it was 2x that form the bonding pies or the anti-bonding pies. It doesn't really matter, okay? Now, a couple other things to pay attention to. So we know that based on this, we have 3 different p orbitals, right? One's going to make a sigma bond, right? This is our sigma bond. And then these two are going to make our pi bonds, right? And we're going to have 2 different pi bonds. And that's why we have 2 boxes here, all right? One, and one set turned into a sigma bond, and one set turned into a pi bond. And then we had one set turning into a sigma, the anti-bonding pi and anti-bonding sigma. Okay. Also notice these energy levels. Now sigma, end over end overlap, is always a higher or a more stable arrangement of making a bond. And so these sigma bonds are going to be at a lower energy level. And so therefore the sigma star is going to be farther up higher, right? Because remember, we talked about how this distance always gets bigger and bigger. As one gets more stable, the other one gets more unstable as you go up in the anti-bonding. Okay, and then the pi orbitals also do the same thing. So the pi guy here, all right, is less favorable than the sigma, right, because it's the sideways overlap as opposed to end-on-end overlap, and so it's going to be slightly less stable than the sigma, okay? And then because it's not quite as far down, the sigma star, or the pi star orbital will be not quite as far up as the sigma star orbital, okay? Now, we say that, but life can act, like, based on this can get, you know, this seems pretty intuitive. Now, there are certain cases where life gets a little bit weird, okay? When you have an s orbital interacting with the pz orbitals, all right, more than the px and py orbitals, you can actually get these guys to flip places, all right? And so you can actually get your sigma 2p and your pi 2p can actually flip places. Okay, so this is them forming your orbital diagrams. Your sigma star goes down here, or your sigma bonding sigma goes down here, your sigma star goes here, and then because of this interaction, your sigma 2p is actually going to be at a higher energy level than your pi 2p. Okay, kind of bizarre. All right, so now this is kind of where the rubber meets the road. So here they've drawn the molecular orbital diagrams for the diatomic molecules in the second period elements. So all the second period elements, boron, carbon, and we've already done lithium. So essentially we're just doing the rest of that row. So boron, carbon, nitrogen, oxygen, fluorine, neon, okay? So notice that we have large 2s2p interactions when we don't have a quite full p orbital, okay? And so when that happens, the pi 2p is actually lower in energy than sigma 2p. All right, and so you can kind of see that, well, that makes sense because you've got your 2 electrons here. It's kind of partially full or half full orbital something. But anyway, so you get this sigma interaction, okay? All right, and then so you can see the bond order is 1 here, bond order is 2, 3, and then it goes back down to 2, 1, 0. Okay, so that makes sense because we know nitrogen is a triple bond and oxygen is a double bond. Fluorine would be a single bond, and neon is a noble gas that shouldn't bond at all, right? Also notice that they also predict the bond enthalpy. Okay, so that as your bond order goes up, that increases, you know, the number, the single, double, triple bond. That should also increase the strength of the bond, right? and so those numbers increase. And then on the flip side here, as your the bond orders go down, the bound enthalpy also goes down. We can see the same trend with our bond length. As the bond order goes up, the bonds get shorter, because we know that single versus double versus triple bonds get smaller, and then they get back bigger again as our bond order goes down. All right. Now the other thing that we want to look at here is this idea of paramagnetic versus diamagnetic. Okay, paramagnetic compounds, and we'll talk about what that means here in a second, are caused when you have unpaired electrons in your molecular orbital. Okay, so this is boron here has unpaired electrons right here, so it's paramagnetic. All right, carbon has no unpaired electrons, everything's paired up. Okay, so it's diamagnetic. Same with nitrogen, everything's all paired up, it's diamagnetic. Oxygen, though, has unpaired electrons up here in the anti-bonding orbital, so it's paramagnetic. And then fluorine is also diamagnetic. All right. Now here's what's cool about that. Diamagnetism, okay, these are the result of all the electrons in every orbital being spin paired. These substances are weakly repelled by a magnetic field. Okay, weakly repelled by a magnetic field. So if it's diamagnetic, it's weakly repelled by a magnetic field. Now paramagnetic fields, compounds, okay, is the result of having one or more unpaired electrons in your orbital. Okay, and these guys are attracted by an electric field, or magnetic field, excuse me. Okay, and so we can see that oxygen here, because it's got unpaired electrons, is paramagnetic. Okay, so here's a picture of two magnets. Okay, and they've got liquid nitrogen. They're pouring between those magnets, and these magnets are super cooled or something. And so this liquid nitrogen comes, it actually forms and gets stuck. Instead of keep going, it just kind of sits there, stuck in the magnetic field, because it's paramagnetic. Okay, now if you did this purely based off of the Lewis structure, you would not be able to predict that oxygen had any effect based on a magnetic field, right? Okay, so but using the molecular orbital diagram, it's pretty easy to see that it is paramagnetic. Okay, so that's the real benefit. One of the real benefits of using the molecular orbital theory is that it allows us to predict paramagnetism in compounds that we probably couldn't have predicted it before. All right. All right. So let's do. Let's see. Let's do a couple of these. Predict the magnetic properties and bond orders of peroxide ion. Okay, so O22 minus, well, really, we can let's just cheat a little bit here. So we got O22 minus. Well, oxygen is right here. If we're going to add two more, so we're just going to sketch here. We're going to say it's O22 minus. That means we're going to add two more additional electrons here. So this is going to become full, right? So we're going to have that guy there. All right. So that means this guy's all full. To find the bond order, right? The bond order of O22 minus, we take 1/2 times the number of bonding orbitals, okay, or the bonding electrons. So 1, 2, 3, 4, 5, 6, 7, 8. All right, 8. Minus the number of anti-bonding. 1, 2, 3, 4, 5, 6. 6. And we get 8 minus 6 is 2 divided by 2, so the bonding orbital is 1. All right, bonding order is 1. Okay, and the bonding, so this guy here would be diamagnetic, right? Diamagnetic, because all of this is completely full. Diamagnetic. And that would be O22 minus. What was the other one that they had in this list here? Whoa! Whoop! Okay, acetylide, excuse me, C22 minus. So let's just cheat again. We'll just go back. That was pretty easy. We'll do that again. All right, C22 minus. So we're going to add two more electrons in. So it'll be like this. Okay, so the bond order for this guy, we'll just jot in a 2 minus here. So bond order. So the number of bonding electrons, 2, and then 4, 6, 8. So it'd be 1/2 times 8 minus, there's only one set of bonds, so it would be 2. So the bond order would be 3. Cool? Cool. Oh, and so then this is completely full, so it would still be diamagnetic. Okay. Diamagnetic. All right. Last little thing here, and I just want you to be kind of aware of this. So far, we have purely talked about homonuclear diatomic molecules, meaning that the diatom is only made from the same element. Okay, we can, that we can make diatomic molecules with with tons of different elements stuck together. It doesn't have to be the same thing stuck together all the time, right? So this is where life gets a lot more exciting, okay, with these molecular orbital diagrams, and they help. And then they start to get real funky. All right, a couple of things that I want you to pay attention to is that because they are from different elements, they come in and their orbitals are going to be at different energies. Generally, the more electronegative element will have orbitals at a lower energy. Okay, so oxygen is a more electronegative, so its orbitals are going to be at a lower energy. Nitrogen is at a higher energy because it's less electronegative than oxygen. Okay, so you can notice that here the 2s here versus the 2s here, even though they're both 2s's, they're at different energy levels because they came from different elements, right? And the 2p here versus the 2p here, okay? Different elements, okay? Now notice that other than that, like the ordering of our molecular orbitals are exactly the same, okay? And so you got sigma 2s, sigma star 2s, sigma 2p, sigma, or pi 2p, pi star 2p, sigma star 2p, okay? Now, one general thing that you should keep in mind, okay, the one that yeah, so this is just kind of how it's set up. You just fill it in bottom to top, etc., etc. You can find bond order, just all the same stuff. The other thing I want you to know, okay, is that this idea down here. It says the more electronegative atom has orbitals lower in energy. Okay, that's true. Okay, so the bonding orbital will resemble them in energy. Will more resemble them in energy. Okay, so that means this energy level of your bonding thing is going to be closer in energy to your more electronegative element, and your anti-bonding is going to be closer in energy to your higher electronegative. And that just makes sense, right? This guy's closer to this than this is to this, right? This line segment is shorter. Okay, and so essentially what you're saying is that kind of affects some of the characteristics of the bond, sometimes the shape of it, kind of change lots of different things. But anyway, that's about as much as I would like you to know about molecular orbitals. It's a totally different, strange world that we took a peek in. Just barely skimmed the top of molecular orbitals. It's pretty trippy, so don't worry too much if it's thrown your mind for a loop. Do those practice problems we've talked about, and let me know if you have any questions. All right, and I'll see you on the flip side.